In this problem, we're looking at a beam of length L, which is clamped to the wall there on the left side at A, supported by a roller there on the right side at B, and we have a line load W0 of force per length, which is acting constantly along the length of the beam. What we're asked to do is find, as a result of the loading that's on the beam, what is the reaction at B and what's the angle of rotation of the beam deflection there at B. We know that we need to start out with our appropriate FBDs, so let's first look at a free body diagram of the entire beam. Reaction forces on the left side of AY, reaction couple there of MA, a reaction force of BY, and we have this line load, which is going to be putting a resultant force of W0 times the length L. From this free body diagram, I'm going to do a summation of moments about A, get minus MA minus W0 L times L over 2 plus BY, the reaction force, times its moment arm of L, and that's a 0. When I sum forces in Y, I get AY plus BY minus the resultant force of the load W0L, and that's equal to a 0. So from this one FBD we get our two equations, and unfortunately, since we have AY and BY and MA all as unknowns, two equations is not enough to solve for our three unknowns. So this problem is indeterminate. So we know that we need to look at deflection analysis in order to get the additional equations that we need to solve. So what I've done here is I've made a cut in the beam. I kept the right-hand side of this. I'm going to let X be the position measured from the right side of the cut. So the forces that we have acting on this, we have BY, we have shear force V, bending moment of M, and this again is there at point E. There's going to be the resultant force due to this line load. Since the length of the section that we kept is X, this is W0 X, and it's halfway between E and the N. One thing to keep in mind is that for part B, we're looking for the rotation there at NB. Using the energy approach, we need to have a couple at any place that we want to know the rotation. So this says that we need to put a dummy couple of M0. The dummy couple means that we'll keep it there until the end, and eventually we'll set M0 equal to a 0. So I need an M0 on both sides here. So based on this, I'm going to write down a moment equation about this point E, and that's going to be the internal bending moment there of M with a negative sign in front. I got W0 X, that's the resultant force due to the line load. It has a moment arm of X over 2 with a negative sign in front. I get BY times X and the dummy couple there of M0. So from this I have what I need, and that's the internal bending moment of the beam, so that's going to be minus W0 over 2 X squared plus BYX plus M0. So this is what we're going to use in our energy expression. So if I look at the strain energy, in the beam, I've got U, which is equal to 1/2 the integral of m squared over EI dx, integrated over the length of the beam. So for part A, what we want to do is find the reaction at B. So the big plan is we're going to calculate the deflection at B using Castigliano. So that's going to be partial of the strain energy function with respect to By. So that's going to be 1 over EI, integral from 0 to L, of M, partial M with respect to By dx. So we take our expression there for M, which is going to be minus W naught over 2x squared plus Byx plus M naught, that's M. I need the partial of M with respect to By, that's simply going to be x. So that gets integrated over the length. So that's going to be, if I carry out this integration, I have it x squared times x, so that's an x cubed. So that's going to be equal to, there's going to be an x to the fourth, which comes out of this. So this is W naught over 8 x to the fourth. I have the integral By, so that's going to be Byx squared, so that's going to be 1/3 Byx cubed. The integral of M naught x, that's going to be equal to 1/2 of M naught x squared. So all this gets evaluated at 0 and L. So doing that evaluation, get minus W naught over 8 L to the fourth plus By L cubed over 3 plus M naught L squared over 2, like that. So this is in general how you go about finding the deflection of the beam at B. But we note that since we have the roller support, we set delta B equal to a 0. From that we can solve for By. We cancel out this. So this becomes that By is equal to 3/8 W naught L minus 3/2 M naught over L. So that's what we get in general. For part A, we know that MO is a dummy load. We don't really need it for this part. So in this case, we set MO equal to a 0. So therefore, we get that By, the reaction force at B, is simply going to be 3/8 W naught over L as that. So that's our reaction. The support on the right side carries 3/8 of the total load acting on the beam. Okay, so now we're asked to find the rotation at B. Using Castigliano, that's partial of U with respect to our dummy load of M naught. So that's going to be equal to 1 over EI, integral from 0 to L, of M, which is Byx, minus W naught over 2 x squared plus M naught. Partial of M with respect to M naught is a 1, so that gets integrated over x. So simply doing my integration, the integral of x gives me a 1/2 x squared. Integral of x squared gives me a 1/3 x cubed. integral of m naught gives an m naught x, 0 to L. So on the right hand side here, you get 1 over EI times W naught L cubed divided by 48. So this is the rotation at the end there on the right. So in summary, for what we have done is that we wanted to use, or we're going to use the energy principle here in order to, one, calculate the reaction force at the right side, and two, calculate the rotation there on the right side. We need to use the energy approach to find the reaction, because the first thing that we discovered from our equilibrium was that we had too few equations for the number of unknowns, 2 equations and 3 unknowns. So we needed to do deflection analysis, the strain energy. We calculate the deflection at B using Castigliano, partial U with respect to By, did the integration. M naught is a dummy load, so from that we got By. And then to find the rotation at B, keep in mind we had to have a couple there at B. So we artificially put a couple there at the M naught, did all the calculations of partial U with respect to M, do the integrations, and then on this very last step here, we set M naught equal to a 0 because we artificially put that load on the end. That's a dummy load. So that's the process that we took.